Okay, so in the last video we took a look at how we could model the force of tension within the framework of Newton's laws of motion. Here we're going to start taking a look at the normal force and gravity. So in this problem here, I have a skier that is going down a 37-degree slope at a velocity of 60 kilometers an hour. And we'll say that the skier is 100 kilograms with all their ski equipment. What I would like to know is what is the force, and we're also going to note that this is a uniform speed. So that means constant velocity. So with all of that, what I'd like to know is what is the force of kinetic friction acting on the skier. Now we'll do more in a bit to model friction forces, but for now let's go ahead and analyze this problem. So whenever you've got an inclined plane kind of a thing here, one of the very first things you are going to want to do is you are going to want to pick your coordinate system so that the x-axis is parallel to the plane. And since if there's going to be any acceleration, it's almost certainly going to be down the plane, you're almost always going to want the plus x-axis pointing down the slope. And that'll be the case here. I can only think of one problem, and it's a very sick and twisted problem in magnetism involving an inclined plane, where you wouldn't want to do this, and in that particular problem you would want to align the y-axis with the magnetic field. But that's the only problem I've ever run across where you wouldn't want to make the choice of tilting the coordinate system so that the x-axis is parallel to the ramp. So, all right, let's go ahead and identify our system. Our system is the skier. Okay. Now let's go ahead and do force identification. The line cuts through the snowpack here, so there will be a normal force from the snowpack, and there will be a force of kinetic friction. It's kinetic friction because the skier is moving. More on that in a minute. Then we ask ourselves, are there any long-range forces? The answer is yeah, there is. There's gravity. So with that, let's go ahead and start analyzing our system. So we'll make a free body diagram, and the normal force is going to be perpendicular to the surface, because remember, that's what that means. And the force of kinetic friction will be parallel to the surface and opposing the motion. And gravity will be straight down. All right, so now let me go ahead and put in my coordinate system here. So again, there's my plus x, there's my plus y. So the reason we do this is you can see by making this choice, the normal force and kinetic friction both lie along axes. So now it's only gravity that doesn't lie along an axis, and that actually means that there's less trig to do. There is a very handy relationship, and you should play around with angles to convince yourself that this is true, but I just view this as another law of inclined planes. This angle and that angle are always the same, so we'll use that fact as well. Alrighty, so with that, we can go ahead and identify here, since these are the only components we're going to be worried about. This is my FGY, and that's my FGX, and I've dropped a perpendicular there. And this angle here is, again, my theta equals 37 degrees. Okay, so here I can write, I'll ultimately be able to write two equations, but but I might only need to write one of them. So you know what, just for the heck of it, let's go and solve for the normal force as well, just so it doesn't feel left out. So since we said that the skier is going down the hill uniformly, that means that the acceleration is 0. So believe it or not, this is an equilibrium situation. We usually call it dynamic equilibrium because the skier is moving. But remember, by Newton's first law, the skier is perfectly entitled to say that they're the one that's stationary and the whole mountain is whizzing past them. So it's just like any other equilibrium problem that you may have done, like, say, looking at, the three-way tug-of-war problem I did in the previous video. All right, so with that, let's go ahead and write down Newton's second law of motion for this. So that's going to be F net equals ma, and here a is 0, so that'll just make our lives a little easier. My forces are the normal force, kinetic friction, and gravity. And that equals 0. All right. Now where I'm going to get two equations out of this to solve for my two unknowns, so I'll be going to the land of x and to the land of y separately. So in the land of x, I can go ahead and look, see, are there any forces or pieces of forces acting in the plus x direction? And the answer is yes, Fgx is acting in the plus x direction, and Fk is acting entirely in the minus x direction. So that equals 0. And then in the land of y, are there any forces or pieces of forces acting in the plus y direction? Yes, the normal force, all of it. And gravity, some of it, minus Fgy. And again, the y component of 0 is 0. All right, so all that's left to do, so actually, we can solve both of these right away. This one's going to give me that Fk is equal to Fgx, and this one's going to give me that Fk is equal, that N, the normal force, is equal to Fgy. So to get Fg, so let's do Fk first. That'll be Fgx. Well, the x component, that's the opposite. So that's going to be equal to Fg sine theta. And so it'll be mg sine theta. So it'll be 100 kilograms times 9.8 newtons per kilogram. Cancel, cancel. Sine of 37 degrees. By the way, if you ever do run across the angles 37 or 53 degrees in a problem, it is the instructor being kind to you in case your calculator failed. That's because they are the interior angles of a 3, 4, 5 right triangle. So technically 36.9 degrees, but that means that, if your calculator fails on a test or whatever, you can go with using 0.6 for the sine of 37, for instance. So anyway, we grind this all through. We get that our force of kinetic friction is 590 newtons. All right. Looking at the y equation, we got that N was equal to Fgy. So it'll be Fg. Again, here this is the adjacent, so it'll be Fg cosine theta. So it'll be equal to be equal to mg cosine theta. So that will be 100 kilograms times 9.8 newtons per kilogram times the cosine of 37 degrees. Cancel, cancel. And that one is going to give you 783 newtons. So notice here that the normal force was less than the force of gravity on our skier. Our skier is 100 kilograms, so times 9.8 newtons per kilogram. The force of gravity on the skier is 980 newtons per kilogram. And this is because the normal force is pushing perpendicular to its surface and pushes only hard enough to keep the skier from crashing through the snowpack. If this seems a little odd at first, just think about what if the skier were going down a vertical cliff. In that case, you could convince yourself that the snowpack wouldn't have to push at all, right? So that must be the case then, that the normal force can vary from, say, the force of gravity or whatever on the person to zero. So having some sort of value in between makes total sense. In fact, the normal force could even be greater than the force of gravity if, say, we had cables pulling down on, say down and into the pack or something like that on the skier or whatever. So the normal force could be literally anything. But in this case, we should be looking at this and be not terribly surprised that it's less than the force of gravity. And same deal with the force of kinetic friction. We should not be surprised that it's less than the force of gravity on the skier either, because it's acting parallel to the surface. Now in this particular problem, I just plain told you that the skier was accelerating at zero, but often we don't have that luxury. So if we need to figure out what the force of kinetic friction is without, or force of friction is without knowledge of the acceleration, then we're going to rely on our models of friction. So let me go ahead and introduce our mathematical models for friction. There are two major regimes of friction. There's static friction. So this means that the two surfaces are stationary with respect to each other. Oops. And kinetic means that the two surfaces are moving with respect to each other. So our skier going down the hill was an example of kinetic friction because the skis and the snowpack were sliding across each other. On the other hand, an example of static friction would be, say, if I just stuck a block on an incline that was covered with sandpaper or something like that, and it just stayed there, that would be static friction. Now, to be fair, there is another regime of friction that you'll run across in some books called rolling friction. Generally speaking, it's, unless you are designing car tires, it's not something that's going to usually be a big factor in a problem. So for this treatment, I'm going to neglect that regime. Okay. So in the case of static friction, so let's start there. So in the case of static friction, the value, because you're just talking about an object that's literally just sitting there. If you think about it here, if you got a block just sitting like this, the force of static friction would be zero. But if it were on an incline, the force of static friction would have to point up, just to up the ramp, just to keep it from moving. So this means that in our model of static friction, all we can do is tell you the biggest possible value it could be. So generally speaking, to find the force of static friction, you need to know one of two things. You either solve Newton's second law of motion for it, or if you're told that it is just about to slide, or similar phrasing, then we can use our model of friction for it. So the value of static friction can take on any value between 0 and Fs max. So this is the biggest value of friction that you can have from the surfaces. So keep in mind the way that we usually say static friction works is no two surfaces are ever perfectly smooth. The jaggies between the surfaces can interlock, and so then the jaggies exert forces on each other. But if you push hard enough, eventually you'll break the interlocks and start moving. You can do this for yourself by just taking, say, your left hand and holding it so the fingers are straight up, your right hand so the fingers are straight down. Slide the fingers in between each other so you're looking at the inside of both of your hands, and then try sliding them sideways with respect to each other. You'll find that eventually the fingers will pop out. So that would be our Fs max. Now it turns out that there are many, many models for friction depending on the surfaces, but you always end up getting the same answers, which is pretty amazing. So it turns out that our value for Fs max is going to be equal to mu static times the normal force. And this gets called the coefficient of static friction. Now notice this is not a vector equation, and this is because the normal force is going to point perpendicular to the surface, and the force of static friction is going to point parallel to the surface. Instead, this is just a relation between the magnitudes. This coefficient of static friction depends on the two surfaces involved and can be looked up in tables. By the way, to draw a lowercase Greek letter mu, if you remember that special paper that we used in like second grade, that's how you draw mu. Alrighty. Now, as far as direction goes, the direction of the force is parallel to the surface and in the direction required to keep the object stationary with respect to the surface. Now, also with these coefficients of static friction, most of the time the values are going to run between 0 and 1, but tires will work by a different model. It turns out that tires actually make a molecular bond with the road, and that they basically unroll off against the road like some double-sided tape. And in the case of compounds used for racing tires, they have achieved coefficients of static friction as high as 20. But for most things, if you're getting values much bigger, bigger than 1, you should be skeptical. And certainly if it's bigger than 20, you should be really worried. Just generally speaking, tires are weird beasts all around. All right. So let's just do a quick example for finding our force of static friction. Let's just imagine that we got a box in the back of a pickup truck. Yes, my pickup trucks look even worse than my cars, so just deal with it. So there's the box, there's the pickup truck, there's the box sitting in the bed of the truck. Let's say the mass of our box is again 100 kilograms, just to keep things nice and simple. Let's say the coefficient of static friction between the surfaces is 0.7, and that we are accelerating forward at 2 meters per second squared. All right, now remember, so what we want to find is what would be the force of static friction required to keep it stationary, and does the box slip? So again, I do a force identification diagram here, and because it cuts through the surface, it'll be both a normal force and a force of static friction, because even though the truck is accelerating forward, the box is accelerating forward with it. So that's keeping the two surfaces stationary with respect to each other. And then are there any long-range forces? Well, yes, there is. There's gravity. So now let's go ahead and draw a free body diagram for this. All right, so gravity down. Let's just go for the low-hanging fruit, right? Normal force perpendicular surface, got to be up to keep it from crashing through the truck bed. Now, pause and ask yourself, which way is the force of static friction going to point on the box? And after you've made your choice, get back with me on it. Okay, perhaps counterintuitively, the force of static friction has to point to the right. And this is because since the truck and box are both accelerating to the right, it's literally the only force we got left. And so what's making the box go forward? The friction between the truck bed and the box. So in order for it to accelerate the same as the truck, the force of friction, static friction of the truck on the box has to be to the right. Now by the third law, the force of static friction of the box on the truck is to the left, and so that's acting to slow the truck down against the road trying to push the truck forward. All right, so with that we can go ahead and start writing Newton's second law of motion for this. So F net is equal to ma. So this will be N plus Fs plus Fg equals ma. And again, here we will go ahead and take components. So the x component is just going to be Fs, and that's equal to ma. And that's literally it. So 100 kilograms times 2 meters per second squared. The force is 200 newtons. And we know it's to the right. We already drew that in. Now, for completeness sake, I did ask, is this going to slip? In order to figure out if it's going to slip, we have to calculate the normal force. So in the y direction here, the normal force is acting up, gravity is acting down. There is no y component to the acceleration, so ma is 0. So we get the normal force is equal to Fg is equal to mg. By our model of friction, the force of the maximum possible value that static friction could be before things start slipping will be mu static times the normal force. So it'll be mu static mg in this case. So it'll be 0.7 times 100 kilograms times 9.8 newtons per kilogram. So that's going to give me 686 newtons. Now, 200 newtons is less than 686 newtons, so we will not slip. If the required force were greater, then the box would slip, and that would take us into the regime of kinetic friction. So let's go ahead and treat that. So with kinetic friction, now remember in kinetic friction, the two surfaces are sliding with respect to each other. And if you did that thing with the fingers I was mentioning earlier, you probably noticed that the fingers are still bumping against each other, so there was still a resistive force, just not as big as it was before. And it turns out that here, again, it's going to oppose the relative motion. And it will always be equal to mu k times the normal force, where mu k is the coefficient of kinetic friction, which will always be less than the corresponding coefficient of static friction for two surfaces. Going with our bumps model, this is just because you're kind of surfing along on the top of the bumps rather than being interlocked in. Typically, coefficients of kinetic friction run between 0 and 1. So to finish this video out, let's just take a look at this example. Let's say I have a block that was initially moving at 20 meters per second, and it comes to a halt. And we'll say that the coefficient of kinetic friction between the surfaces is 0.5. So I would like to know how far does the block slide. Now you might say, hey, wait a minute, you didn't give me the mass. Well, this is why doing things with letters is good. A lot of times with problems that involve gravity, because of the fact that we cancel inertial and gravitational masses against each other, a lot of times you can have a problem where if you aren't given a mass, you'll find that although you have to put m's in everywhere, they eventually cancel out. So let's just hope that's the case here. So again, force identification diagram. So we've got the normal force and now kinetic friction. Long range force is gravity. Let's draw a free body diagram. So here we'll have normal force up, gravity down, kinetic friction to the left. Now we know the acceleration is going to be to the left, but since my direction of positive x is implicitly to the right in the problem, because looking at the kinematics, you're saying this is x equals 0 and this is x, we're going to want to pick our coordinate system to be the standard up, down, right, left here. So plus x plus y, like that. All right, so then we will have that the normal, so we can say F net equals ma, so it'll be the normal force plus gravity plus kinetic friction equals ma. So again, we can take the y component of this and get that normal force minus gravity equals 0, just like before. So this is n equals fg equals mg. And in the x direction, we will have that ma is equal to minus fk. Well, by our model, this will be minus mu k times the normal force. This is minus mu kg. Oops, mg. Oh, hey, look at that. ma, mg, the m's cancel. You get that a is minus mu kg. Now from there, we can look at this and say, oh, hey, this is a missing t situation, so we can do kinematics on it. So we can say v squared equals v naught squared plus 2a x minus x naught. Our final v is 0, our initial x is 0. So we get that x will be equal to minus v naught squared over 2a, but our a was minus mu kg, and we can cancel those. All right, so now we can go ahead and put in the numbers. This will be 20 meters per second squared over 2 times 0.5 for our coefficient kinetic friction times 9.8 newtons per kilogram. But here for balancing units, probably better to restate as meters per second squared. So in the numerator, I have meters squared per second squared. In the denominator, I have meters per second squared. So I lose all my seconds and 1 power of meters. And I am left with my block sliding 40.8 meters. Awesome. All right. In the next video, we'll spend a little bit of time talking about drag, elasticity, and maybe do a couple other little things. So catch you later. Have a good one.